First of all, we're going to look at investing money, regular installments. There's these things called annuities. What are they? It's basically compound interest investment. But instead of making one, you're making continual ones. And you can see here, payments are made or received on a regular basis. So it might be every year, maybe every month, every fortnight, whatever, for a fixed period of time. Now, different types of annuities. We've got what we call an ordinary annuity, and that's when you deposit the same amount at the end of the compounding period. And so that would be like a loan, because you would pay it back at the end of the compounding. You wouldn't pay it at the start, because that doesn't make sense. You take out a loan, and as soon as you take it out, go, oh, here's my first repayment. Doesn't make sense. So that's what we call an ordinary one. And then there's an annuity due, and that's when you pay it at the beginning. And so that's more when you're investing rather than when you're borrowing. So superannuation. For instance, you put it in, and then it's in for a month, it gets compounded, and you make some money. Future value then. So that is the total value of investment at the end. So the value of it in the future, what it will amount to. Present value is this. If instead of putting continual payments in, you decide, no, I'm just going to put one lump sum in at the start, and then that's it. I'll just leave it there. How much would I have to put in at the start to get the equivalent, as if I was to do it in? So that's what we call present value. Now, it's an unfortunate thing, but banks have this product called annuities. And yes, they are annuities, but it's not the only type of annuity. So just be aware of that when you are actually out there thinking, oh no, hang on, there are different types of annuities other than the product that the banks call an annuity. Okay, let's have a look at an annuity due then. 2002 question. We have a superannuation fund that's going to pay 8.75%. Now, of course, it's a very simplified problem because superannuation funds don't usually have a consistent interest rate for the whole term because they're placing the money in investments, and so one year you might get 10% on your money, another year you might actually lose money. I mean, it can happen with superannuation funds. So it's a simplified model. We're going to assume here 8.75% compounds annually. $5,000 in the fund at the beginning of every year, commencing on the 1st of January 2003. So what will the value of this superannuation be when she eventually retires 20 years later? Okay. So this is how we set it up. You see, every one of these investments is a compound interest problem. And so we just say, well, what are all the different compound interest problems? So the very first one we put in will be in there for actually 21 years. Because you'll see she retires on the 31st of December. So there's actually 21 years that money will be in there. Then, of course, the following year she'll put another amount in, but that'll only be in there for 20 years. And then the next year she'll put one in, it'll be in there for 19 years, and so on and so on and so on, until the very last year. At the start of the last year, she'll put $5,000 in, and it'll just be in there for 1 year. So a whole series of different compound interest problems there. Basically, our amount is going to be the sum of all of them, but we saw that compound interest is like a geometric term. So we have a sum of a geometric series. First term is 5,000 times 1.0875. I know it's the last term, but I'm makes it easier to put the smallest one as the first term. The ratio, 1.0875, and there are 21 terms there. Plug it into our sum formula, and there we go. There's our final amount. $299,604.86. So that was the actual HSC question. Now, I've expanded on it a bit, that's why there's an asterisk there. They didn't actually ask these questions, but let's make it interesting. So find the year when the fund first exceeded 200,000. So ended up with almost 300,000, but when was it? It was first over 200,000. So the amount is, there's that series that we created, but the difference now is we don't know which year was the last one. So we want to find n basically. The sum to n has to be greater than 200,000. We just have our inequation to solve here. We need to make n the subject of all this. So let's play around with it. Multiply by 0.0875, divide by the 5,000 times 1.0875, move the 1 to the other side, log both sides, bring the n to the front, This time it's a log bigger than 1, so the sign will stay the same. So n has to be greater than 17.16, etc. So n would be 18. So 2021 would be the first year. Here's another interesting one. $1 million. Everyone thinks of $1 million. So how much should she have put in if she wanted $1 million rather than the almost $300,000? This time, same series, but this time we don't know what P is. We don't know the principal. How much are we investing? That's what we want to find this time. Okay, and we want that sum to 18 to be $1 million. Just an equation to solve, bit of rearranging, and there's the amount. So $22,818 every year. But how much is that a week? It's a lot of money, isn't it? Well, I suppose if you want to try and build it to $1 million in just, 20 years, 19 years, you're going to have to put a fair bit in at the start of each year. So the future value of an annuity due, the future value, that's basically what we just worked out. The future value, how much did it end up being? We could create a formula then. Future value would be, there's all the terms, and so if we plug that into our sum to n terms of a geometric, we would have that. Now, unfortunately, you can't quote that. Okay. Oh, well, P is of course principal, R is 1 plus interest rate, N is the time periods. Let's now do another part to that same question. If Stephanie could afford it, how much money could she save by making one investment? So now we're working out present value. What would the present value be? How much today will end up with that amount in 21 years' time? So we're saying PV to the power of compounding interest has to end up to be the same amount of money. 54,467. So if we could scrape that money together, I'd only have to put in, or not me, Stephanie would. Stephanie would only have to put in that amount of money at the start, and she'd still get the same amount. So the present value of that investment is 54,467.64. So how much did she actually save? The actual investment, she ended up putting in 21 payments of $5,000. So actually invested $105,000. She could have just put in $54,467 today if she could scrape the money together, saving herself like $50,000. So if you can scrape it together, that's even better. Right. So let's create a formula for present value then. And what we're saying is present value in the compound interest formula, we want that to equal the future value. But we worked out a formula for future value. So let's play around with this one and make PV the subject, and that would be a formula to work out the present value of the annuity due. Again, P being principal, R being 1 plus our interest rate, N the time periods, and so on. Sometimes to make life easier, they just give us a table of values. They say, oh, just read off this. They've done all the calculations for us, and we just have to work out how to use it. So we've got two people. This is for an annuity of $1, so then obviously you multiply it by however many dollars you're investing. So Tim and Janine, 6% per annum, 4 years. Tim's going to invest $1,500 each quarter, compounded quarterly. Janine's going to go $500 every month, compounded monthly. Who's going to get the greater amount of interest? So Tim is 6% per annum, but we need to use our table. So 6% per annum, it's compounded quarterly, so it'll be 1.5% per quarter. So we're in the 1.5% column, and how many time periods would we have? Well, it'll be there. It'll be 16 time periods, 4 years, 16 quarters. So that gives us our 17.9324, but we're investing, where was it? There it is, 1,500. So there's the future value, 26,898.60. Janine was 6% per annum, but she's going monthly, so that's 0.5% per month, and the number of months for that one would be 48 months. So 54.0978 times by 500, she's investing 500, would be 27,000. So Janine would actually end up with more money there. But it was the interest that we're interested in. So Tim's interest would be, well, the final amount minus how much he's invested, 2,898.60, and Janine, $3,000 interest. So she ended up with $150 more than Tim. Okay, so 14D.